Drop a feather and a hammer from the same height. Everyone knows what happens. The hammer hits the ground first. Why? Because the hammer's heavier, you say. All right, but what does that actually mean? Does being heavy make Earth pull harder on it? Does being light make something fall slower? And here's the real question. What if there was no air at all? You've been told your whole life that heavy things fall faster than light things. That's not physics. That's just describing what you saw. It's a label, not an explanation. The truth is, what you think you know about falling objects contradicts 2,000 years of common sense. The misconception isn't that heavy falls faster. It's about what falling is. For 2,000 years, scholars believed Aristotle. He said heavy objects fall faster because they seek their natural place, the earth, more vigorously than light objects. It seemed obvious. Drop a stone and a leaf. The stone hits first. Therefore, heavy things must want to reach the ground more than light things do. But I asked a simple question. What does it even mean to say an object falls more vigorously? That's philosophy, not measurement. So I did something radical. I measured. I dropped balls of different weights from towers. I timed their falls as carefully as I could with the instruments available. According to Aristotle, a 10-pound ball should fall 10 times faster than a 1-pound ball. That's what the theory predicted. But that's not what happened. They hit the ground at nearly the same time. There was a slight difference, yes, but nothing like what Aristotle claimed. The scholars said I must have measured wrong. My timing must be off. The balls weren't dropped simultaneously, so I repeated the experiment. Same result. Again, same result. The weight of an object does not determine the speed at which it falls. That much was clear from direct observation. Then the question became, if weight doesn't control falling speed, what does? Let me show you why Aristotle's logic fails. Imagine you have two balls, one heavy, one light. According to Aristotle, the heavy one falls fast and the light one falls slow. Yes? Now tie them together with a string. What happens? Think carefully. The light ball should slow down the heavy ball, like a drag. So the combined system should fall slower than the heavy ball alone. But wait, you've just created a single object that's heavier than either ball was individually. Shouldn't this heavier combined object fall even faster than the heavy ball by itself? Both can't be true. The logic contradicts itself. Either the light ball drags the heavy one down, or the combined mass makes it fall faster. Aristotle's framework forces you into an impossible position. Well, unless weight doesn't matter at all. Here's what actually happens and why. All objects, regardless of their weight, fall at the same rate when there's no air resistance. Not because they're pulled with equal force. That's not it. The Earth does pull harder on heavier objects. But here's the key. Heavier objects are also harder to accelerate. Those two effects cancel exactly. Think about it this way. Push a cart. Easy enough. Now load the cart with bricks and push with the same force. The cart accelerates slower. Why? Because it has more mass. More mass means more resistance to acceleration. Gravity works the same way. Earth pulls the brick harder than it pulls a feather. The gravitational force is proportional to mass. But the brick also resists acceleration more than the feather does. That resistance is also proportional to mass. The force increases with mass. The resistance increases with mass, and they cancel. Net result. Same acceleration for both. I proved this with inclined planes. I rolled balls down ramps which slowed the motion enough that I could measure it carefully. I marked positions, timed the motion with a water clock, recorded everything. The acceleration was constant, the same for every ball, no matter what it weighed. Every ball, every time. The measurements didn't lie, so why do we see the hammer beat the feather in real life? If gravity treats them the same, why don't they hit together? The answer isn't gravity, it's air. Air pushes back on falling objects. That's air resistance. And air resistance doesn't depend on weight the way gravity does. It depends on shape, on surface area, on speed. A flat feather catches a lot of air relative to its mass. A dense hammer doesn't. Same gravitational acceleration, completely different air resistance. The feather gets slowed down drastically. The hammer barely notices the air. That's what you're actually seeing when you drop them, not different responses to gravity, but different responses to air. Which raises a question. What if you removed the air completely? What if you could drop a hammer and a feather in a perfect vacuum, with no air at all? In 1971, an astronaut on the moon did exactly that. David Scott stood on the lunar surface, held a hammer in one hand and a feather in the other, and dropped them simultaneously. The moon has no atmosphere, no air resistance whatsoever. They hit the ground at exactly the same moment. Exactly, not almost, not close, the same instant. This is what I predicted in 1638 when I published my work on motion. It took 333 years to test my prediction in a true vacuum, but there it was, direct confirmation. The church condemned my book. They said it contradicted scripture and common sense. How could a feather fall as fast as a stone? Everyone could see that wasn't true, but I had measured, I had calculated. The mathematics didn't care what seemed obvious or what ancient authorities claimed. When you measure carefully, you discover that nature doesn't behave the way human intuition expects. Aristotle trusted his eyes. I trusted my measurements. Once you strip away the complications, the air, the friction, all of it, you see gravity's true character. It accelerates everything equally. So what is falling, really? It's not about objects seeking their natural place. It's not about heavy things pulling harder. Falling is acceleration, the rate at which velocity changes over time. Near Earth's surface, everything accelerates downward at about 9.8 meters per second. That's what the number means. Drop something. After 1 second of falling, it's moving at 9.8 meters per second. After 2 seconds, it's moving at 19.6 meters per second. After 3 seconds, 29.4. The speed builds continuously. Doesn't matter if you drop a feather or a cannonball. In vacuum, both follow that same acceleration. What changes in air is how far they get before air resistance stops them or significantly slows them down. Want proof you can do yourself? Take a clear tube, put a feather and a coin inside. Seal one end, attach a vacuum pump to the other end. Pump the air out. Now flip the tube. The feather and coin fall together, perfectly synchronized. Let the air back in. Flip it again. Now the coin wins, because air resistance affects the feather more. Same tube, same gravity, same objects. What changed? Only the air. That tells you air resistance was the difference all along, not gravity itself. Now here's something fascinating about the distance objects fall. It doesn't increase linearly with time. It increases with the square of time. Let something fall freely for 1 second. It drops about 5 meters. Let it fall for 2 seconds. It doesn't drop 10 meters. It drops 20 meters. 3 seconds, not 15 meters. 45 meters. The relationship is mathematical. Distance equals 1/2 times the acceleration. Times squared. In symbols, d equals 1/2 gt squared. I proved this relationship with inclined planes, slowing the fall enough to mark exact positions and measure exact times. The pattern was unmistakable, or put it another way, the speed keeps building so you cover more ground. Each second, then you did the last second. First second, you accelerate from 0 to 9.8 meters per second. Second, you accelerate from 9.8 to 19.6. You're moving faster on average during that second, so you cover more distance. The acceleration is constant, but the distance traveled each second increases because you're already moving. So gravity accelerates everything equally. That much I could measure, calculate, and prove. But here's what I couldn't answer. Why? Why does Earth pull objects toward it at all? Why does the gravitational force depend on mass in exactly the right way to cancel out mass's resistance to acceleration? I measured how things fall. I couldn't explain why they fall. I discovered the pattern, not the cause. Newton later showed that gravity depends on both masses, Earth's mass and the object's mass, and that the force weakens with the square of the distance between them. That's why the object's own mass cancels when you calculate acceleration. Earth pulls harder on heavier objects, but by exactly the amount you'd expect from their mass. So the acceleration ends up the same. But even Newton admitted he could calculate gravity's effects perfectly without being able to explain its cause. He called it action at a distance and found it philosophically troubling. How does Earth reach across empty space to pull on the moon? He didn't know. He just knew that it does, and he could predict the result. I showed that falling is acceleration, not heaviness, that the speed of falling doesn't depend on weight. That was revolution enough. I changed what people measured and how they thought about motion. The deeper question, the nature of the gravitational force itself, that wasn't mine to answer. What changed because of this work? Before, natural philosophers trusted, received wisdom and obvious appearances. If Aristotle said it, and if everyday experience seemed to confirm it, that was enough. After, there was a new method: measure, calculate, test under different conditions. The hammer beating the feather isn't wrong exactly. It's incomplete. You're not seeing gravity alone. You're seeing gravity plus air resistance. Those are two different effects. Combined, separate them, as on the moon, and you see gravity's true character. Everyone sees heavy things fall faster. I asked, what are you really seeing? Is it gravity itself, or is it something else? Turns out it was air resistance masking gravity's actual behavior. Once you isolate the variables and measure each one separately, you discover what's really happening. This method, identify the factors, isolate them, measure them independently. Test predictions, this became physics. This is how we study nature now. Aristotle looked at the complex world and made philosophical arguments about natural places and inherent properties. I stripped away the complications and measured simple situations. Rolling balls down ramps, dropping objects in as controlled away as possible. Timing everything carefully. The simplicity was deliberate. Find the basic pattern first, in the clearest case. Then add complications back one at a time and see how they modify the basic behavior. That approach, more than any specific result, changed everything. So the misconception isn't that heavy falls faster. In air, it does fall faster, or at least it hits first. The misconception is thinking that observation tells you about gravity. What you observe in daily life is gravity filtered through air, resistance, friction, and everything else that complicates real motion. Gravity itself treats everything equally. That's the hidden truth. You have to strip away the complications to see it. Why does Earth pull objects at all? What is this force? I measured its effects precisely. I could predict exactly how fast something would fall, exactly how far it would travel in a given time. But the cause, the mechanism by which Earth reaches out and pulls, I had no answer for that. That mystery took another 50 years and a man named Newton to make real progress. Even he couldn't explain the why, only the how. He could calculate it perfectly, predict it precisely, but he couldn't say what gravity is, just what it does. I got the falling part right. I showed that it's acceleration, universal and equal for all objects. I demonstrated that weight and falling speed are independent. I established that careful measurement reveals truths that casual observation obscures. That was enough for one lifetime.